proportional reasoning style problem. Okay, so we'll just make one up here. So let's say that we have two masses separated by some distance. Okay, so two masses, m1 and m2, separated by a distance r, and a force F exerted between them, which is just Newton's universal gravitation. Now we're going to change some of the parameters. So we'll, let's say that we'll double the first mass, we'll triple the second mass, and then we will half the radius between them. How does the force change? So it's that sort of question. All right, so first we look at the original case. So we'll call it F1 for the original case. It would be G m1 m2 over r squared. It's just Newton's universal gravitation. All right, so we're going to change it. We're going to do G, and then we agreed that it would be twice the first mass, 3 times the second mass, over 1/2 the radius. We half the radius, that goes inside the exponent, inside the square there. Okay, so we're going to bring all these new coefficients we've added outside of the equation. Okay? So we'll write our G again. And we've got 2 times 3, which is 6, over 1/2 squared, which is 1/4. So 6 over 1/4. And what's left over here is the m1, m2 over r squared, which we'll recognize as being F1, right? So 6 over 1/4 is 6 times 4, so it's 24 times F1. So how does the force change when we double the first mass, triple the second mass, and half the radius between them? The force is 24 times greater. Okay? This is how I like to think about these. Just get those coefficients in there, and then bring them out, factor them out. Don't forget to square that half. Bring it out front, figure out what your coefficient is, and then what you're left with is universal gravitation, which is the original, which is F1. There you go. So you should be able to do any combination of things. So like you could quadruple the first mass, take 1/3 of the second mass, and change the radius by 5/9 the radius or something like that.
Will you ever be affecting the force and then trying to find force?
Sure, we could do that. So let's say that the question is, got two masses and there's a force exerted between them and the force doubles, but the masses are the same. Then how did the radius change? We could do that. And to do that, we would just rearrange the equation. Okay? So originally, we have F1 equals G m1 m2 over r squared. Let me just call it that. All right. And we want to figure out, what did I say? The force doubles. We need to figure out how the radius changed or something like that. Okay. All right. So we just need to rearrange this for radius. So radius squared would be G m1 m2 over f. Okay, so let's go ahead and put those coefficients in. So m1, m2 are the same, and then we've doubled our force. Okay, so we're just going to bring that out front now. Bring that 2 out front, so it becomes 1/2 times G m1, m2 over f. We'll recognize G m1, m2 over f as being the radius squared. So 1/2 the radius squared. Then we can just root the whole thing. So we wind up with 1/4 the radius. Wait, does that make sense?
What?
No, it's not 1/4 radius.
No, it's not.
Screwed that up. We'll take it back here. Let's finish it. Let's do this right. We'll do root G m1 m2 over f. Okay. All right. So now we're going to make that 2f change. So it's 2f. So we've got r equals root of 1/2 G M1 M2 over F. So R okay, so we've got a root the half. What's a root of a half? 1 over root 2, yeah. So we got 1 over root there. That makes sense. 1 over root 2, G M1 M2 over F. So we would need to change the radius by 1 over root 2 in order to double the force. Because of course this is just 1/2 over root 2 times that force. All right. So that's the proportional reasoning style problems. So
I can't find it.
you can't find it? Don't worry about it. It's in there somewhere. I'll look for it if I have a minute. It's a good question. That's why I wanted to give it to you guys. All right. The second style problem is the multiple masses. You have to figure out the net force on a mass. So, is there an example from the textbook we could do for this one, or do you want to just make up one? They don't really give you a whole lot of questions here.
Who's your number 4 on page 141?
Okay, so that's exactly what we just did. It's a proportional reasoning problem. So I'm going to let you work on that one, okay? And work on it with Darren. You two work on it, and then get back to me, okay? Because I think you could do that after. Just apply the same method we just did. Okay. All right, well, we'll just make up one. Let's say that we had a system with 3 masses. Mass 1, mass 2, and mass 3. And they're at fixed points of the triangle, so they can't move. And we want to determine the net force acting on M1, let's say. Well, let's say that they can move, but we're not interested in that. We're only interested in the net force, and then who cares about the motion after that? Because if they're a fixed triangle, then they would be exerting, there would be a frame exerting forces, so forget that. So it's just a mass. M1, there's 3 masses on a table, they're all lead balls, they all exert forces on each other. Okay, so we start this by drawing a free body diagram for the mass of interest. So what's the net force on mass 1? Well, we know that mass 1 will feel an attractive force towards M2, and will also feel an attractive force towards M3. Let's assume that all the masses are the same for this. So there's our free body diagram, just 2 forces acting on it. And if we had to guess some kind of acceleration vector, it would probably be accelerating in that direction, but we're not going to care about that. We just care about the net force here. All right, now because we're given a triangle in the question, we'd have to be given some information about the triangle. So we might be given some dimensions to the triangle. So maybe that's 5 or 3, or it's 9. And their meters is pretty big, but whatever, just for simplicity. Okay, so if you're given those sides of the triangle, then you can find your angle theta. Once you know that angle, then you know this angle here as well. Choose either angle you want, and then we can write out Newton's second law for mass M1. So let's do that. And we're going to assume that up and right are positive, because that's the direction the vectors are heading.
Up and left?
Up and left, yeah. Thank you. I usually do right. That's why I said right and drew left. Okay. So, some of the forces on 1 would be equal to the force of 3 on 1 plus the force of 2 on 1. All right, and now we're going to write an x and y version of this equation. So some of the forces in the x will be F31 in the x plus F21 in the x. That's 3 on 1 and 2 on 1. And then the sum of the forces in the y for body 1 will be F31y. And then there is no y component for this one because it's just horizontal from the first mass.
So you resolved the force of F31?
Well, yeah, I've only resolved it into x and y here.
Okay.
I haven't put in the sign of the cos
Okay.
yet. So let's continue to work on our equations here. Okay, so the sum of the forces on y and the x will be F31x, which would be F31, and I'm going to use I'll use this angle up here. F31 sine of that plus F21. F21x is the same as F21 because it's horizontal from M1. And then for the y components, it's just F31y, which is F31 cosine of that angle. Okay, we don't need real numbers in here, but those are your equations, right? So you have to find these forces, F31, F2, and F21. How do we find those forces if we know all the masses and the distances between the masses? How do we find them? Universal gravitation, right. So over here, we're going to go ahead and do that. So F21 will be G N2 M1 over R21 squared. F31 will be G N3 M1 over R31 squared. This is all known information. So that means that we can find F21, F31. And this theta, that's not theta, sorry, that angle is also known. We can figure it out with geometry. So that means that we know all these values. So we know the x and y components of our net force. So now it's just a matter of drawing.
Please excuse this interruption. This is just a test of the PA system. Please disregard this announcement. Thank you.
Test of the PA system. Okay. So Fx is going to look like this. Some of the forces in the x. Some of the forces in the y is going to look like that. So this would be F1x. So some of the forces in the y there. And our resultant vector will be the net force. So we would just use Pythagorean theorem to find this. And then to find that, we would just use inverse tangent, or whatever you want, because you know all the sides. And that's how you find the net force. Now, let's say that I did ask you for the acceleration. How would you then find the acceleration of M1?
Could you not just use Newton's second law and you do
Yeah,
Maxwell's
exactly. If I
acceleration?
then asked you for the acceleration, then you could just use Newton's second law. So the forces equals the mass times the acceleration. This would now be known. This is known. Then you can solve for the acceleration. And would the acceleration be constant or non-constant? Would it change or would it be the same a second later, let's say?
No,
It wouldn't be constant. Why would it change?
Because it's getting closer together, so the radius shrinks and it'll increase the...
Yeah, that's right. As this thing approaches the other bodies, it gets faster and faster, but its acceleration increases as well. So it would would not be CAPM. That's right. Okay. So that's the second type of UG2 problem.